Earth is our planet, home to billions of people and beautiful places. Here's a big idea. Earth is also a chemist. Industrial chemistry has both blessed and cursed our world. It makes products like medicines that save lives, while releasing pollution that can cause disease. But imagine a world with all of the benefits and none of the harm. In that world, we produce chemicals using ways the Earth teaches us, processes that replace hazardous materials with ordinary water. We see Earth doing this on a massive scale, like in Yellowstone Park or places on the ocean floor. Could field geology be showing us a path to better industry? Here at Arizona State University, we want to build that world by combining chemistry and geology to make chemicals in much better ways.
I'm Hillary Hartnett, and together with Ian Gould, Charlene Estrada, and Kurt Robinson, and others, the big idea we have is to turn our research on hydrothermal organic geochemistry into something we call geomimicry. So what's that?
Well, chemistry was developed by humans in laboratories at the conditions we live in, room temperature and sea level pressure. Chemists can now make fantastic new materials, but they often have to use dangerous or toxic chemicals to make it all work. For this reason, chemical factories are a maze of pipes and tanks engineered to properly contain everything and shuttle away waste. But scientists are now discovering chemistry in very non-human environments, deep underground. Earth does amazing chemistry, using mostly hot water and rocks, and recycles everything it produces. A pollution-free chemical factory. This got us thinking about completely new ways for us to do chemistry, geomimicry. Here's an example. This is isooctane, an important fuel for cars and airplanes. Chemists manufacture isooctane using large quantities of concentrated sulfuric acid. After producing isooctane, we're left with acidic sludge waste that has to be thrown away, carefully. Earth makes isooctane too, but it doesn't need sulfuric acid, so it doesn't produce sludge. How? Deep underground, high pressures keep water liquid at higher temperatures, called hydrothermal water. Exotic to us, but normal for the Earth. Hydrothermal water has amazing properties. For example, it produces its own acid from the water, so chemicals like isooctane can be made without needing sulfuric acid. In geomimicry, we can use hydrothermal water to make isooctane, then just cool it back down. The acid converts back to regular water and the isooctane floats to the top. Safer ingredients and less waste. This is exciting. But there are still many basic research questions. For example, in our lab we have seen harmless chemicals suddenly do useful chemistry in hydrothermal water. How many chemicals like this are there? Which are the useful rocks that can catalyze this chemistry? How do we scale from lab to factory? We expect challenges. New processes might produce new kinds of waste. We'll need to minimize harm to maximize sustainability. But we see geomimicry leading a new industrial revolution that changes how everyone thinks of chemistry, from a necessary evil for modern living to a benevolent contributor to well-being. How long will this take? Some things will be quick. They're happening in our labs right now. But technological revolutions require many people working together to make generational change. As more teams research geomimicry, the next generation of industrial chemistry will get better, safer, and cheaper. Geomimicry represents a convergence of ideas from geology, chemistry, and engineering. Scaling it up will also need developments in education, policy, and economics. Geomimicry cuts across almost the entire range of NSF disciplines. Biology is inspiring novel engineering. Our big idea is for geology to redesign chemical manufacturing.
We see a better future where geomimicry, which learns from the Earth, advances our society to sustainably deliver a better quality of life for everyone. Our planet is truly inspiring. Now let's stop imagining and start making the future together.